So suppose that you have a city or a small town somewhere, and somebody went up to the board and said, "Hey, I've noticed that the more that people eat ice cream, the more likely they are to drown." And they have the data. They have the data to support this, and I am including the data in the description of this video, so you can actually pull up the data. It has 700 records of people who have eaten ice cream and drowned, and people who have eaten ice cream and not drowned. And it has an additional variable in there that we'll talk about here in a second. So you are the local epidemiologist, and you ask for the data from the person who presented it, and they give it to you, and you are going to analyze it, and you are good at what you do. And before your boss puts out some sort of advisory to not eat ice cream because it increases the odds of drowning, you decide to do some analysis. And so the first analysis that you do is that you want to know if eating ice cream, yes or no, leads to drowning, yes or no. And you see that the 177 people ate ice cream and drowned. 38 people ate ice cream and did not drown. And you see that 307 people did not eat ice cream and did drown. And 178 did not eat ice cream and did not drown. So you calculate the odds of drowning, given that you ate ice cream, and that is 177 over 38. And you calculate the odds of drowning given that you did not eat ice cream, and that is 307 over 178. And this is 4.66, and this is 1.72. And you do an odds ratio where you divide one number into the other, and the odds ratio is 2.70. So eating ice cream increases your odds of drowning 2.7 times. And you do a statistical analysis in a statistical software, and you find that the p-value for this, or the probability that this is just by chance, is less than 0.05. So it is actually statistically significant. So just looking at the raw data, you determine that yes, eating ice cream does lead to drowning, but that's not the whole story. Example here, where your p-value was significant, you did see an increased odds of drowning given that you ate ice cream. Being the good epidemiologist you are, you also know that there is this thing called confounding. That if you have some unknown variable that is influencing the ice cream consumption and the risk of drowning, then this variable is actually what is causing those two. It is not ice cream to drowning. If you cannot find this variable up here, then this is the causative way. And if you do find it, then it's actually the confounder, not the drowning. So you get curious and you look at the data. And again, the data is in the description of this video. And you realize that they included the dates of these events. So the date that somebody ate ice cream and whether or not they drowned. And you look and you see a pattern because you're an epidemiologist. And the pattern that you see is that there is something going on here whereby temperature, or rather summer, is influencing, because the more people eat, the more hotter it gets, the more people eat ice cream, and the more people will swim. And you wonder if the summer is making things here, or explaining things as to what is going. So you do an analysis, and your analysis is this. You look at the summer months, and you see, again, ice cream, yes, no, drowning, yes, no. And you see that you have 162 people who ate ice cream and drowned, 156 who did not eat ice cream and drowned, and 18 who did not eat ice cream, did eat ice cream and did not drown, and 21 who did not eat ice cream and did not drown. And right away, just eyeballing it, you can see 18 is very close to 21, and 162 is very close to 156. And the odds here is the odds of drowning given that you ate ice cream is 9. And the odds of drowning given that you did not eat ice cream is 7.42. And your odds ratio for this is 1.21, or you have about 21% higher odds of drowning given that you ate ice cream. And being the good epidemiologist and by a statistician or a person who paid attention about statistics, you by statistical analysis and you find out that the p-value here, the probability of it just being by chance, is 0.61, not statistically significant. So this association that you're seeing here is not statistically significant. It is likely explained by chance. Actually, 60% likely that it is explained just by chance alone. So you continue your analysis and you look at non-summer months. So peak, off-peak times. And again, this is using the same data. Yes, no, and drowning, yes, no. And you find that 15 people who ate ice cream drowned, 151 people who did not eat ice cream drowned, and you find 20 people who ate ice cream did not drown, and 157 who did not eat ice cream did not drown. The odds here is 0.75, so you have actually a protective effect. If you eat ice cream, you're actually less likely to drown. And for this is 0.96, also a protective effect. Anything on an odds less than 0 is actually more of a protective effect because your odds ratio is 7.78. So you had about 22% less odds of drowning if you ate ice cream. And interestingly, here the p-value is also more than 0.05. It's actually 0.59. So this is not statistically significant. So you went from a situation in the previous, but here this stratifying by month, by time of the year, actually showed you that it is not statistically significant. And this is what we call stratified or adjusted for this variable, adjusted for the confounder. And so if you see your raw measure of association, in this case odds ratio, is different, so this is an equal sign that's supposed to be like that, is different from the adjusted, then you have to look for confounding. There are other mechanisms that could be at play, but we're not talking about those. That's for a more advanced biostatistics class. So what do you do? How do you say for sure that the actual, what do you say are the actual odds given this? And so for this, we use what we call the Cochran, Mantel, Hansel method. And what it is a complicated, a little bit of a complicated formula that looks a little bit like this. You take the sum of A1 times, it's a complicated formula. It's even complicated for me. A1 D1 or DI for the different levels over NI. And it's the sum of all that over the sum, this is supposed to be the sum of everything, the sum of B2, C2 over NI. So what do we mean by A, D, B, C, all that? Well, remember those 2x2 tables that I was making, the ice cream and the drowning? And then this is yes and this is no, this is yes and this is no. This is A, this is B, this is C, and this is D. And remember that I stratified it by summer and non-summer. And so for the non-summer, for the summer, that is, let's see, for the summer, A is 162. Let's do it another color. 162, 18, 156, 21. And for the non-summer, it looks like this: 15, 20, 151, 157. So what I'm going to do is move this equation over to the side. Let's see here. There we go. And now let's do our equation. So 162 times 21 over 700, no, not 700, 357, sorry, which is the number of people in the summer, plus 15 times 157 over 343, and 343 and 357 is equal to 700, so we're good. Again, the data are in the description. And we divide that by 18 times 156 over 357 plus 20 times 151 over 343. And after you do the math, you come up with 16.395 over 16.6702, which is equal to 0.98. So this is your adjusted odds ratio. So taking into consideration the differences in summer, you actually have 2% less odds of drowning if you eat ice cream at any time of the year. So there is, and then you do the statistical analysis, and this p-value is actually 0.95, so not statistically significant. So overall, there is no association between drowning and eating ice cream, or between ice cream and drowning. The true association is summer. So when you do the same calculation and you adjust for eating ice cream or not, summer is what is causing the drowning. So that is something that you need to keep in aware when you're looking at data, when somebody is giving you data. And the data do show that among those 700 people, the association was there and it was statistically significant. But once we stratified or adjusted for or accounted for the differences in seasonality of both eating ice cream and drowning, it all went away. And you see this all the time in many other studies. If they fail to adjust for confounders, or if there are confounders in there that they did not recognize or could not recognize or could not account for, then the conclusion could be a little bit flawed. And you need to keep that in mind. When somebody presents you with evidence, right, ask yourself, did they account for all the confounders? Did they use advanced statistical methods? Or were they lazy and just presented you with the raw odds ratio? Which unfortunately, a lot of armchair epidemiologists, people who did not study epidemiology, did not study biostatistics, are doing now with the immense quantity of data that is up there. So download the data. If you want to do this yourself, you can do it on Excel, you can do it on R, you can do it on Stata, SAS, whatever you use for statistical analysis. Let me know if I'm wrong. I'm always open for discussions and for corrections. And thank you for watching.